This week in your studies, you're going to see a whole bunch of wireless technologies, and some you are going to be familiar with, others you are not going to be familiar with. And I thought it might be instructive to go over some of them, not all of them. Certainly there are many more wireless technologies than the ones you see here, but I thought it might be interesting to see how some of them work, dig into some of them just a little bit, and get basic ideas so that the words don't just look foreign to you when you see them. So let's get going. Zigbee is sort of an alternative to Bluetooth or to Wi-Fi, and it's used primarily to control IoT devices like smart light bulbs and smart furnaces and refrigerators and so on, and also medical device monitoring. Now, in order to use Zigbee, you have to have a Zigbee network, and it consists of a coordinator, which you see right up here in this red box, routers, which you see here in this blue box, and then the end devices that are connected to them. You can see sort of a schematic of what that looks like here, where this red circle is the coordinator, and these blue circles are Zigbee routers, and then the Zigbee end devices. Now, how is this all put together? Well, the Zigbee coordinator, which you see over here on the right-hand side, is just plugged into an Ethernet LAN port. So, in other words, you have a wired network of some sort, and this comes off of the wired network and plugs into that, and that becomes the coordinator, and there's only one coordinator in your network. Next, you have to have some Zigbee routers, and these are typically wired for power. As you can see, this goes into the wall here and is wired, but the receiver and the transmitter of the signals are wireless. In other words, from the coordinator to the routers, and then from router to router, these are all transmitted wirelessly. The only reason we need the wire here is to power the thing, because this is a relatively low power, but if you only had standalone devices, you'd have to be changing batteries all day long. You wouldn't want to do that. And then finally, of course, are the end devices, quite often, as I said, smart devices or medical devices, which we would run on this Zigbee network. Now let's take a look at RFID, radio frequency identification. It is often used in stores to track product. For example, if you walk out through a sensor, there's probably an RFID tag that was deactivated before you walked through that sensor, and that tag can alert the store that something's being taken out. Or it can be used for inventory. It can even be used at the checkout stand if everything in the store is tagged. These can be paper-thin tags. In fact, they can come as labels that you can just stick on things. However, in order to use RFID, you need three parts. You need the RFID tag, which you see over here on the right, and then the reader, and then the back-end server, which that reader either connects to wirelessly or is plugged into. Now, here's the interesting part. The tag is a little computer, but it has no power. You see this big long line that spirals around on this tag? That's the antenna. It's a big old long antenna, and then the little computer bit is right there in the middle, the little blue square with the black outline. That's the actual computer in there. So it's got this horrendous antenna. Well, why does it need that long antenna? Well, the reason is that it is actually a computer powered by the signals, the RF energy given off by the reader. So, in other words, rather than being plugged in, it's getting its energy from the reader itself, which is bombarding this tag with radio frequency energy, and then it just makes this chip sort of boot up quickly, if you will, and send the information back then to the reader. Now, RFID can be read from anywhere from a few inches away to 1,500 feet away, although that's kind of a theoretical number. It'd be difficult to achieve. There are passive and active RFID tags. Active ones actually do have a battery built into them. Passive ones do not. Active RFID, maybe 450 meters, but passive RFID, usually 3 or 4 feet is about all that you can get, up to 6 maybe. Remember that these numbers vary greatly with design and frequency. So it depends on how we put this thing together and the frequencies that we use, and there's quite a different number of frequencies that we use, and so we can get quite a range of different numbers. This is only an example number, this 3 feet here. An RFID tag, as I said, is a tiny computer chip that is powered by the energy from an external antenna which is on the reader. So the reader supplies the energy for the tag. RFID has an interesting history. Although it was only patented by Charles Walton in 1983, it dates way back to the mid-1940s by a man named Leon Theremin, who was forced to invent it under duress by the Russian government. You may recognize his name. The theremin is this musical instrument that responds when you move close to the antenna. Now, NFC is a related technology to RFID. In fact, it works on the same general principles, that is to say, the power being supplied by the reader by RF energy, but the power levels generated for NFC are vastly lower than they are for RFID, and so it must be powered very close to the computer chip itself. Now, you've seen these, of course. They're on your credit cards and debit cards today. The little computer here, which is a little chip on your card. Sometimes these are called a smart card because it's got a little computer on it. And that little computer is powered when you get close to this RF signal here, either coming from one of these tap-to pay stations or when you insert the card into a card reader. Now, one nice thing about this is that it can hold your credit card information encrypted so that the employees at the store never have access to your card number and expiration date and all of that kind of information. It does cut down on theft, especially insider theft, because the store doesn't ever see the number. That number is recorded encrypted, and only the bank or the credit union has the key to unlock that code. Now, this is a fascinating one. LiFi. This is just a takeoff from the name Wi-Fi. Wi-Fi is not an acronym, so this doesn't really have an acronym either. But the LI in this case just means general white light. And it is generated by LED lamps. So the idea is to have an LED lamp and then a receiver here. And this is actually encoded by very subtle changes in intensity of the light. And it turns out that you can change the intensity of that light from these LEDs very rapidly. And because these LEDs are putting out a specific frequency, the receiver is able to make out what is and what is not encoded light from this LED lamp. So that's how we encode it. And it turns out that we can get exceedingly fast information transfer from this technology. The reason we can get such fast information transfer is because the visible light spectrum are at frequencies way above the radio frequencies that Wi-Fi and other things operate on. As a matter of fact, it always strikes me as a little bit humorous when you hear somebody talking about 5G and how 5G is dangerous because the frequencies are so high that it's going to, give us cancer or whatever. And yet we walk around all day bathed in visible light, which has frequencies way above 5G. So it doesn't scare me much to have 5G. There are a couple of interesting TED Talk demonstrations, and I've got the URLs listed here, and I'm also going to put them in the description of this video so that you can find them easily if you want to. This picture is taken from one of them. I don't remember which one it is, but this picture is taken from one of those TED Talk demonstrations. Microwave is a totally different technology. It is a lower frequency technology than some of the others, and because it's a low frequency, you remember from our first week that we said low frequencies can travel very far. Now, they can't carry a lot of information because there aren't a lot of ups and downs in low frequencies to carry that information, to encode it. However, these things can go anywhere from 6 to 30 miles under the right conditions. 6 is easy, 30 is a little harder, but then they can be repeated, as you see here, for long distance communication. Now, one problem with microwave communication is you really need line of sight communication. This is really nice for installations like one I saw not too long ago at a campus, a college campus, where there was a road between the main part of the campus and one of the buildings, and it was a public road, and they were not allowed to run cable over or under the road. So they put up a couple of microwave antennas on buildings across the road from each other, and they were fairly high up in the air, and then they just beamed the information across these two microwave antennas. Worked very, very well. But because this line of sight is necessary, once we get these long distances, such as 6 miles, 30 miles, and so on, now we have to be careful to maintain that line of sight, and it's not direct line of sight. We actually have this thing called a frontal zone. The frontal zone is this football-shaped band that you cannot encroach upon if you want communication to exist. You can block up to 40% of the frontal zone's radius, and still get good communication. But 60% of this frontal zone's radius must be kept clear. Now, if you're curious how you know what this frontal zone shape looks like, I've given you the calculation here where R1M center here simply refers to the radius in meters at the center. And then we have the lambda, which is the wavelength of the light that we're transmitting. And then finally the distance, this small d over here, the distance between the transmitter and receiver. So in other words, it's a function of the wavelength and the distance. But we have another problem. As we get farther apart, in other words, these 30 miles, for example, we now actually have the curvature of the Earth interrupting our line of sight. And so you have to get these things taller and taller and taller in order to get a good signal as you get them farther and farther away. WiMAX at first glance appears to be just Wi-Fi. The idea of it is that here we have an ISP, and here they have a big old tower, and they are generating communication across this tower to the buildings that are nearby. This is something we call a metro area network, or MAN. Now, we don't see too many of these in the United States today. As a matter of fact, I really don't know of any. There might be one or two, but these are highly used in Europe. So the idea of a WiMAX network is simply to broadcast to a community or to a metro area. Of course, that means a couple of things. It means higher power levels. So we have to generate a pretty high frequency. For that reason, by the way, we can't just use Wi-Fi. We can't just beam out a very strong Wi-Fi signal, because Wi-Fi at 802.11, by the way, and WiMAX is 802.16, would violate the FCC's regulation on the power that we can use for 802.11 signals. And so we have to use higher power, and we have to use some licensed bands, some licensed low frequency bands, as you see here. But it will allow community internet connectivity. One of the reasons we don't have it in the US anymore, when we've experimented with it a little bit, is because LTE and 5G on our cell phones has been so successful that it has replaced much need for metro area networks. Now finally, just these last three. HyperLAN is a European version of the US's 802.11 Wi-Fi. VHS radio is also a long-distance, like microwave, version of FM radio operating at 3 to 300 megahertz. That's a very low frequency, so it's often used for long distances like ship-to-ship or ship-to-shore communications, maybe 30 to 50 kilometers. Millimeter wave is the very high frequency technology behind 5G, autonomous vehicles, and much IoT technology. So when you see millimeter wave, it's not a technology in and of its own. It is used by various other technologies today, and we are getting higher and higher frequency stuff because we can get more and more communication on it. Of course, we lose distance. It's a very small wavelength, and as we've said before, very small wavelengths fizzle out very quickly, and they are absorbed by walls and things very quickly. So it is a small wavelength, and it really kind of requires line of sight communication. And because it doesn't go very far, we're only dealing with nearby signals. We're not talking about any long distance for our millimeter wave technologies. So these are a few of the wireless technologies that you may not have known how they worked, and hopefully this was a little bit helpful in helping you understand the technology behind some of it.